Shall I start?
Yeah.
Okay. Imagine you're in a business review meeting and your VP asks, what were the top 3 product categories by revenue last quarter and how did they trend month over month? You confidently fire up your BI tool only to be swallowed by a maze of unfamiliar table names, cryptic column aliases, and a tangle of join conditions. 20 minutes later, you have a query that sort of works and your VP is already on to the next slide. What if instead you could simply ask that question in plain English, right in Slack or in your internal chatbot, and instantly get back the SQL you need, executed and visualized? No more wrestling with schema docs or more tedious debugging. That's the power we'll unlock today with a robust text to SQL pipeline. Hi everyone, I'm Drishti, machine learning engineer at CRED, and welcome to this NIAT masterclass on designing text to SQL pipelines for modern data infrastructure. If you've ever felt the frustration of translating business questions into SQL only to watch your demo stall at the first syntax error, you're in the right place. Over the next several segments, we'll unpack the foundational concepts you need: schema linking, chain of thought prompting, and candidate discrimination. Secondly, we'll examine why pre-LLM approaches buckle under real-world complexity. Thirdly, we'll reveal our LLM-powered pipeline that reliably turns natural language into executable SQL. Fourth, we'll dive into advanced patterns for scaling, cost control, and security in the enterprise. Fifth, finally, close with real-world case studies showing dramatic time savings and ROI when we adopt text to SQL. Let's get started by taking a peek at what we are going to build. Moving to the screen now. As you can see the screen, this is the final product of what we are going to build. There is the part where we can put in the question, and there is a sample set of questions already presented. Then there are the advanced settings. Now you can see in the advanced settings, this is the part where we generate multiple SQL, and you can set how many SQL you want to generate and then discriminate based upon which is the correct one you want to select. Then there is the database type. You can select among Postgres, SQL, SQLite, or MySQL. So depending upon which company you're working for, they can have different set of database, or even the line of business can have a different database type. Then we can choose how many relevant tables to select. So if you are having joins on at most 5 tables, joins on 11 tables, you can select how much it is, and based on that, the system will will keep it in mind and generate it accordingly. Finally, there is the confidence threshold, which is used to select which table, like how accurate and how relevant a table we want to select for this question. So we can try to generate a query. Let me select a question. For example, let's say list all pending orders with customer information. I select generate SQL query. It is generating SQL query. It takes about 15 seconds to 20 seconds in order to generate the queries. And we'll see finally there are 4 components in this pipeline. There is the part which generates the table descriptions. There is the part which selects which is the relevant tables for the SQL query. There is the part which is going to generate the multiple queries, and there is the part which is going to select which is the query which is the best for this question. So for example, you can see that the best query has been selected, and there are multiple queries that have been that were generated, and out of which the best one is selected. We are using DeepSeek as the model which is selecting this model, because it's a great deep reasoning model. And now we are set, and let's go ahead and build this. Now, before we begin the session, let's review the prerequisites you should have in order to follow along and get the most out of this session. So you'll need Python 3.10 with OpenAI, SQL Alchemy, and Rayserve installed. You'll need either Jupyter Notebook or VS Code with Python support. You'll need a SQL Lite instance, which is populated with sample tables. This is needed because we will have the mini dev database from the BERT dataset. Then you'll need OpenAI API credentials or equivalent LLM access. This could be either Claude if you want more context length. Then we'll need DeepSeek API credentials. This is very important because it's a reasoning model and it is great at reasoning, and it will be needed for the discrimination phase. Then we'll need a Snowflake account. This is because we will be accessing the Spider Snow dataset for testing your Rayserve endpoints. So let's grab your coffee, settle in, and let's transform how your teams interact with data one conversational query at a time. Ready? Let's get started. Before the era of large language models, text-to-SQL lived in a world of parse trees and brittle templates. Let me sketch the classic workflow. We had the parse tree generation. Your natural language question is parsed into a syntax tree. Each node corresponds to SQL constructs like select, where, join, group by, order, and things like that. Then we had the separate clause handlers. So it was a rule-based extractor which walks through the tree to fill select clauses, then where clauses, then group by clauses, and so on. Templates stitch these partial clauses into a final query. The following figure helps us understand the workflow. So say the question that we've been given is select customer name where the balance is greater than 3000. So the parse tree would be something like this. It would have the natural language question. It gets broken into the verb phrase. The verb phrase gets broken into two separate parts, the select phrase, the where phrase. Then the select phrase goes into the select syntax. The select phrase also gets distributed into the attribute phrase. Then we get the correct attribute, which is the customer name. So the where phrase gets distributed into the where clause and a conditional phrase. The conditional phrase gets distributed into attribute, condition, and a value according to the line. This generates the final SQL query, which will be select the customer name where the balance is greater than 3000. But this rule-based approach quickly falls apart with even minor changes. A simple schema drift like renaming a column can cause your handlers to misfire. Introduce a new abbreviation, say rev instead of revenue, and your parsers break. And every new domain brings a fresh set of handcrafted rules. This is exactly why we switched to LLMs. Instead of relying on brittle logic, we learn patterns from data, making them far more adaptable. Let's now explore how the pipeline transforms once LLMs enter the picture. With GPT-style models, we can replace these brittle handlers with flexible, example-driven stages. Here's our 5-stage modular pipeline. There's metadata enrichment, schema linking, chain of thought reasoning, and SQL generation, candidate discrimination, and finally the web interface, which brings all of these pipeline things together. Starting with the input question, we get a natural language question. This is fed into the web interface. This is going to be, our model is going to put this on the port 8080 on the local host. The web interface calls the pipeline, which has 4 components. The first component is the table description component. The table description component basically is going to generate the table descriptions whenever you add new tables into the database. The second component, basically given a question, extracts the tables that are relevant for the question. And finally, the text-to-SQL generation service is going to generate the SQL. The final service, the discriminator service, is going to call the text-to-SQL generator service multiple times, and finally it is going to score the different SQLs and select the one which is the best, and that completes the pipeline. Each stage is its service, so you can optimize, monitor, and scale them independently. No monolithic spaghetti code. In the upcoming labs, we'll prototype each stage, then stitch them together into a production endpoint. But first, let's get hands-on with SQL query generation with OpenAI. This hands-on lab is our playground for basic GPT prompting. Here's what you need before you dive in. A Jupyter Notebook environment with OpenAI SDK installed, a minimal database schema, 2 tables, products and merchants, each with a handful of columns, OpenAI API credentials. Now, before we dive into the code, let's understand the workflow. we have the first section which imports the libraries. Then we have the second section where we create the sample data. So in section 3, we define the business questions. In section 4, we set up the OpenAI API. In section 5, we construct the prompt. And in section 6, we generate the SQL using AI. Now we will proceed to implement the following. This is our lab with SQL query generation with OpenAI. Once we have imported our required libraries, Pandas, OpenAI, and OS, we'll proceed towards creating the sample data. First, we create a merchants table using the Pandas data frame. Then we create a products table using again the Pandas data frame. Now we proceed to the third section where we define some business questions. I've put in some example questions like which products are sold by tech store. Next we move to the section 4. We get the OpenAI API key. I've set the API key in an environment file. You can put in your own API key over here. We set up the client for OpenAI key. And then finally, we construct the prompt. In the prompt, we use the different tables, the merchants table and the products table, and we use the example questions to ask it to generate the corresponding SQL. Finally, in the section 6, we send the prompt to OpenAI and get the response. There, as you can see at the bottom, for each question, the OpenAI has generated the corresponding SQL. It's as simple as that. In this section, we covered the following. We set up the data by creating sample relational data using the Pandas data frame. We did the API integration by demonstrating how to integrate OpenAI's API to generate the SQL queries. We did prompt engineering. We explored how to craft effective prompts tailored for SQL generation tasks. And we did business questions by showing how to convert natural language business requirements into SQL queries using the AI. Now, what's next? To build on what we've done, you can modify the sample data and business questions to test different scenarios, or experiment with alternative prompt structures to observe changes in output. Validate the generated SQL queries by running them on real databases. As you continue, you'll send your prompt to GPT and analyze the SQL it generates. Notice how a simple few-shot prompt can guide the model effectively. However, this approach has limitations when applied to real-world datasets. It lacks schema-level context and can't resolve ambiguities in metadata. That's exactly what we'll address in the next hands-on lab. In this lab, we step up to a local MySQL instance loaded with the BIRD mini-dev dataset. We'll work with 14 tables, each with about 10 columns and having around 1,000 rows per table. Now, why BIRD? It's complex enough to simulate real schemas, multiple foreign keys, and varied column names, yet small enough to run locally. What are the prerequisites that we'll need? A running MySQL server with the BIRD mini-dev schema loaded. Your Jupyter notebook is configured with a MySQL connector and the ability to call GPT for metadata enrichment. So we'll start with setting up the environment and database discovery. This we'll do through SQLite connections, DB discovery, question datasets, and OpenAI setup. Once we've done the database schema exploration, we'll do the schema analysis. We'll get the table info. We'll look at column details and the row counts. Then we'll do the AI-powered SQL generation. This will be through prompt construction, LLM interaction, SQL generation, and the query validation. Then we'll move towards a moderate complexity database. This will be the Formula 1 database. Over here, the question will require multiple table joins, domain knowledge, F1 qualifying rules, and 14 tables. Finally, we'll move towards a challenging complexity question on the student club database. Over here, there will be complex joins, temporal filtering, duplicate handling, and 8 tables. Finally, we'll move towards the advanced techniques that are required in order to solve the challenging complexity question. Here, we'll use the AI table descriptions. These will be AI-generated descriptions, which will include the semantic understanding and meta-AI approach. We've gone through the code flow. Let's go and actually implement it in our Jupyter notebook this time. We start with importing all our required libraries. Then we will load the actual databases that are there. This code is primarily doing that. We see there are about 10 databases, and we'll be going through some of them and looking at the questions through them. Then there is the minidev SQLite JSON. This JSON file has all the questions that are related to these databases. So for example, over here, there is the question ID, there is the DB ID. So this particular question is from the debit card specializing database. And the question is, what is the ratio of customers who pay in EUR against customers who pay in CZK? And then there is evidence. Let's get into that in a bit. So first, let's set up the client with the OpenAI, similar to how we had done in lab 1. Okay, so we have the question. We know what the database is from the question itself. It is in the debit card specializing database. So let's explore the database a little bit and try to understand what's there in that. So I've connected using SQLite to the database. Then I've gotten the rows, and using the connection through a cursor, I am going to execute getting the information of the table. So I get all the rows, I get all the columns, and I count the rows and the columns. So I get information that there is the table, customer tables, the gas station tables, products table, transactions _1K table, SQLite sequence table, and year month table. Each of these has around 3 to 4 columns. The transactions _1K table has 9 columns and 1000 rows. So this gives us some information about the debit card specializing database. Now let's go into one of the tables, say the first one. So say the gas stations table, and look into some of the rows of that table. Okay. So we get some sample data from the gas stations. The columns, there are about how many columns? There are 4 columns. There's a gas station ID, chain ID, country, and segment. So we get some information about the data set from the data set here. And we can get even a little more data, that is the schema of the this particular table. So when I look at this particular query, I ask it that, and it tells me that the gas station ID is an integer and it's a not null value because it's the primary key. Then I get the chain ID, which I get to know is the integer and it can be null. Similarly, the country is a text, it can be null. And then there's a segment, which is also a text and can be null. Now, similar to the lab 1, we will have the prompt. So what is the prompt? It says, given the table schema and their sample data from the database debit card specializing, write a SQL query to answer the question. The question we had already stored in the question info, if you remember, and we specifically, it's a dictionary and the part question from the question info. And we are telling it to also provide the chain of thought for the logic. Why are we doing it? Because the question is complex enough that if we ask it to provide the chain of thought, it is going to give us much better SQL query. So as we said, we send it the schema using the cursor execution over the SQL query, and we also give the sample data. This is the same code which we had previously used in order to get the information about the table schema and the information for the row samples. I'm using over here GPT 3.5 Turbo. It's the same as we had used in the lab 1 as well. And as content to the system, we are telling it's a helpful assistant that writes the SQL queries. So let's see, it has generated the SQL query and it has also told us how it is going about it. And so this helps us understand that this is the query. So now what is there is that let's try to parse this SQL query and get the actual result of running this query on the database. So when we do that, we get 2 rows with currency CZK, currency EUR. Great. Now let's check if this result in fact matches with the SQL that was provided for this particular question. So there is a gold data set. The minidev SQLite.json was actually also having the gold SQL. Let's compare with that and if it gives the correct one. Okay, so we run that particular SQL. What is the result? It gives 1 row and the ratio for that is 0.065. And it is nothing like the 2 rows that we had gotten. So we had gotten 2 rows in the previous question, and both of them were incorrect. So why would this happen? Let's see. Now this was still at a simple question. If we move to a moderate question, what would happen? Let's choose a moderate question. We chose a question. This time the database is of Formula 1. The question is, please list the reference names of the drivers who are eliminated in the first period in race number 20. We are given some information which is called as the evidence and the gold SQL, and the difficulty is mentioned to be moderate. So over here, let's do the same thing. Let's explore the database Formula 1. We find that there are 14 tables in it. The tables have like around, roughly on an average, you can say like 10 columns, and the number of rows in this would also be on an average around 1000. So let's do the same thing what we were doing previously. We give the table schema and their sample data from the database Formula 1. Write the SQL query to answer the question. We have changed the question to modify for the moderate level 1, and give the chain of thought for the logic. Sounds great? Okay, we get the SQL query similar to last time. We ask it to execute the query and compare it to the execution of the gold SQL query. And what do we find? The results don't match. Okay, so it doesn't work in the moderate case either. All right, so now let's try some different idea. What if I tell it that give the chain of thought for logic and use only 5 drivers? So what I've done is I've given this evidence also. What is the evidence? The evidence is this external domain knowledge which is explaining things about the question. Let me go back and actually see what the evidence is. Let's go back. Okay, what does that say? It says driver reference name refers to the driver ref column. The first qualifying period refers to Q1. Drivers who are eliminated in the first qualifying period refers to 5 drivers with max Q1, and race number refers to race ID. So it is providing information and context about how to actually solve the problem, which is very, very critical. Now, let's see if doing this is going to solve the problem. So it generated an SQL query. But how can we tell if it is correct or not? We have the results that it generated, like what are the correct results using the gold SQL query, and what is the results that it generated. Is it correct? No, it's not. So we need to do something even more. When we have to move to a challenging question, what do we find? We find that, keep in mind that these things, if you try to run multiple times, you might get different results, and some of the SQL queries might actually be correct. Please remember that fact as we'll proceed to the candidate discrimination phase, and we'll handle that particular controversy. Okay, so we're moving to the challenging complexity. Over here we look at, I've already selected a question where the difficulty is challenging. That particular question says, what are the names and income amounts of members who both attended events and received income on September 9, 2019, and this is from the database student club. So let's again do the same thing, explore the data set. We get around 8 tables. The number of columns are on our average are around 7 to 8, and around 1000 to 2000 rows per column, per table. Okay, now let's do the same thing what we were doing. We give the table schema and the prompt, we give the sample data from the database, we give the question, we give the external knowledge that was needed for the question, and we ask it to give the chain of thought for the logic. So we get the SQL and we compare it to the gold SQL results. What happens? It does not match, not at all, not even in the far case. So now what do? I have an idea. What if that for the prompt, it is becoming very difficult to do a lot of tasks in the same case. It has to not only ascertain which tables and columns are relevant, it has to also generate the SQL query. So let's try to do something. Let's try to distinguish these two components. We'll keep one part where we tell it to generate the tables which are relevant, tables and columns which are relevant for the question, and then given these tables and columns, we'll ask it to use these tables and columns to generate the final SQL query. And it seems like, given that we have broken down the task for an LLM, it should be easier to form the correct answer. So over here, we say given sample data of tables from the database, we give the question at the database, select the names of the minimum tables and relevant columns needed to answer this particular question. And in the content for the system, we tell it you are a helpful assistant that analyzes tables. When we do that, it says that it's the members table, and the columns that are relevant is first name, last name, and the income table with the amount. Now, this cannot be correct because if we look at the question talks about the event as well, and it should have in also gotten the event date table, but it has not done that. Okay, so that itself was not enough. So maybe the LLM is having a difficult time trying to understand the table relevance based simply on the schema of the table. So I have another idea. Let's try to generate table descriptions, and from those table descriptions, we'll ask it to generate the correct and relevant tables. So once we do that, let's look at the prompt for doing that. We say you are provided sample data from a table in the database of student club. You want to generate the table and column descriptions in a JSON format as follows. Don't provide anything else. So I'm asking it to generate the JSON format, and it to tell it the table description, give it the table description, give the column data and saying column 1, column name and the column description. And finally, I'm providing it the sample data for each table to generate the table description. Okay, so I get the descriptions. I'm storing it in a dictionary again for each table called the descriptions table. Now, finally, I'm telling it that given the table schema and the descriptions of the tables from the database formula 1, this should actually be student club. Okay, so write the SQL to answer the question and giving the external domain knowledge also for that particular question. Once I give it that, it generates an SQL also. And let's see if the SQL is correct or not. This time, the SQL is incorrect. On this lab, we'll see how to go through the different SQL on the BERT minidev database, and let's get started. So in the last one, we are seeing that we have run it on the challenging complexity question, and the result is slightly different. As I mentioned, sometimes the challenges of the LLM is that it behaves sometimes a little unpredictably. You can set the temperature to be different and try it out, but like we saw that I am running it again for the previous complexity questions, and I find that the answer comes out correct. Let's see that. So when I tried for the simple complexity question, I tried it again, and when I ran it again, this time I got the correct SQL and the correct answer for that. So I am specifically showing it over here. So when I ran it with the chain of thought, it gave the correct answer. The ratio between the two is 0.07, whereas for the gold SQL, it was 0.0657, which it has rounded off to 0.07, which is fine. And similarly, for the moderate level question, after the when we did the external evidence, firstly it was not giving the correct answer at all, but after giving the evidence, then when we checked it, it gave the correct answer. So still sometimes, as we saw previously, it was not giving the correct answer. This time it is giving the correct answer, but at least we are getting somewhere closer to the correct answer. So as we are adding in new techniques, we are finding that the accuracy of the pipeline is increasing, and we are getting closer and closer towards getting the correct SQL. And here finally, in the final case, when we see, we get the correct answer, Sacha Harrison, which is with the amount 50, but we are still missing on Carlo Jacobs. Let me try this one more time with the schema and descriptions. So over here, we still find that this is not giving us the correct answer. Perhaps you can go ahead and try playing with the LLM with different prompts and trying to see which one gives you the correct answer. We'll pause this particular lab over here and proceed to the next one and more techniques where we can try to get the correct SQL at the one shot itself. And we do not have to iterate it multiple times in order to get the different SQL. So let's try and proceed towards that. Let's take a moment to recap what we've done so far. In the first lab, we did a simple OpenAI GPT prompt to get the natural question into a SQL query. In the lab after that, what we did, we went through the BERT minidev database and we went through different complexity questions. We went from simple question to moderate question to a challenging question. And in each question, we saw that we were trying to put in new techniques in order to improve the accuracy of the SQL that was generated. As we know, LLMs can hallucinate, and we want to make sure that the SQL that is generated is correct so that the final results that we get are also correct. Now, in order to tackle the challenges that we faced in the previous lab, we will proceed to a new lab where we will be handling these challenges. And one more thing we'll be doing is we'll be moving towards a much larger data set, the spider snow data set. Over here in the real world, what we find is that there are more than 14 tables in a database. More often than not, you will be working with around 100, 200, maybe even more than that, like 1,000 tables at a time. And so what we've done is provided a script to help merge the spider snows dataset into around a 150 tables dataset, and we'll be working on that in the following lab. So here we'll be tackling schema linking at scale using a merge subset of the spider snow dataset. The scripts for that has been provided. So first, we'll do the environment setup and dependencies, which is going to be OpenAI, the Snowflake connector, the sentence transformer, pandas data frames, scikit-learn, and the requests in library. Then we'll get into the database connection to the Snowflake and the schema discovery of that particular data set. Then we'll look at this question data set and we'll look at the specific question that we are going to handle over here. Finally, we'll do data sampling and analysis. We'll look at the JSON-L file processing, the spider dataset, the database matching, the question filtering, and the natural language questions. Then we'll proceed to have the AI-powered table description generation. We'll take the sample data extraction, do the statistical analysis, do data distribution insights, and look at the average columns per table. Now, when we'll find some issues over here, so we'll proceed towards semantic embeddings and clustering. Over here, we'll do GPT 3.5 integration with JSON descriptions, table documentation, column meanings, AI-generated metadata. We'll proceed towards sentence transformers, use k-means clustering, semantic embeddings, and question-to-cluster matching with cosine similarity. Finally, we'll do the SQL generation and validation, where we'll do multiple SQL generation through GPT 3.5. Then we'll use DeepSeek to validate and select the best SQL and do the final query extraction and refinement. So in this lab, we'll be working with a dataset which will have 150 columns, roughly about 120 tables, and about 100 rows per table. Now, we'll be approaching the table description and table relevance in a two-phase manner. Firstly, we'll do the coarse pruning, where we'll use clustering of the tables in order to find how the tables are semantically related to one another. Then we'll select the cluster which is the most correct for our particular question and do the table relevance upon that particular question. This is going to prevent the GPT from drowning in tables and also help us to scale for even larger data sets. Let's get started. Okay, in this particular lab, we'll start with importing these libraries, OpenAI, as we have always been doing. This time we'll need sentence transformers for the semantic embeddings, and we'll use the requests in order to access the DeepSeek API. And Snowflake connector in order to access the Snowflake because the data set is too large to be in a local SQLite. So, I hope you will set up your credentials for your Snowflake account and put these credentials in your config. Once the config is set up, you can test the connection and make sure that you can connect to Snowflake. Once we have that, let us explore that by using the select query, where we'll go through the information schema tables and see which are the base tables. So it looks at 151 tables and some of those are sampled over here. The naming is a little strange, but that is because I have merged these from the spider snow data set. The merging has gone from using the AdventureWorks as the database, the AdventureWorks as the schema, and then country, region, currency as the data as a table within that. So we have merged it from the different like around 15 databases to get 151 tables into one database, which is very often what will happen in the real world companies. Let's go through one of the tables, say the first table, and look at how many columns there are. So we use the query, select column, data type is nullable, column default, all things we have previously done in the previous lab itself. We do that and we find that there are 3 columns and 100 rows. Now, for each of the spider data set, you will find a spider2snow013.jsnl file. This particular file contains all the questions. There are around 500 questions that are related to this data set. We can pick one particular question, and over here I have put in this particular question SFBQ011, which is the question instance. The question itself says how many distinct pseudo users had positive engagement in the 7-day period ending on 7th January at so and so time, but had no positive engagement time in the 2-day period ending on the same date, January 7th, 2021 at 11:59:59. As you can see, this is a much more complex question that we have been seeing before. Let's see how we can tackle this. The external knowledge for this has also been provided. First, we want to make sure that the question that we are looking at is in fact is from the database and the tables that we have selected when we merged from Snowflake. We selected one particular question. Let's say we selected the question SF local 009. Over here, I have chosen this particular question. You are free to choose any question of your choice. I chose this question because it had around 4 joins from 4 different tables. Now, the database it requires is airlines. Over here, this airlines database has a few tables, only around 10, but we have merged to around 150 tables. Let us see whether our algorithm will indeed be able to pick up the correct tables or not. The external knowledge is coming from this Haversine formula.md. Why? Because the Haversine formula is used to compute the distance between flights and cities. So that counts as our external knowledge. It is quite similar to how we have done in the previous lab itself. Let's take the tables and sample data from them in order to generate the table descriptions as we have done in the previous lab, as we have found that for the complex questions, we need the table descriptions in order to generate the table relevance. So over here we find that just an average count of the columns is around 117. That's a lot of columns. So you can find that in one go, you cannot actually describe all of the columns. So if you were to give all the table schemas in one shot and ask it to generate table descriptions, it will not be able to do so. The prompt will exceed the context length. That is why we'll go table by table. So we create our OpenAI client. We give it the data. We are sampling data from the table, and we ask it to generate the table description and the column description over here. Similar, but going one table at a time. And we tell the context, you are a helpful assistant that analyzes tabular data. Now, as you can see, when you run this on your own, this can take you from 7 to 10 minutes in order to run this, as there are 151 tables and 151 corresponding prompts being sent to the OpenAI API. Okay, now once we have the descriptions of the tables, we want to select the minimum number of tables and relevant columns that are needed to answer that particular question, along with the extra information that is there from the markdown file. And we also tell it to format the response. We send this format and it tells us it selects airlines flight. Okay, now and it selects just one table. Now looking at the gold SQL actually takes airlines flight and airlines airports data as well. So it is taking 2 tables which it has not mentioned, and it has selected only one table. What could be the reason? Perhaps the LLM is getting confused by having so many descriptions in one shot in order to decide which is the correct table. So we introduce a new method to overcome this. That's the method of semantic embeddings and clustering. The idea is that among these tables, what you can do is you can cluster them based upon their semantic meanings. So we take the sentence transformer model, the all mini LM L6 V2 model. You can choose a different one, but I personally prefer this one for creating sentence embeddings. And table descriptions should fit our sentence embeddings greatly. So we take the table names and generate the table descriptions using the table name plus the description. And use this model to encode that and generate the table embeddings. I have done that and finally stored it into a dictionary. Next, we want to cluster these into different clusters based upon their semantic meaning. And this will happen even in a large company. Sometimes you create tables for one particular case, sometimes you create tables for another particular case. Once we have generated the semantic embeddings, we want to group the tables into different categories based upon their semantic meanings. Why? Because even in a real world database in any company, you will find some tables are relevant for one particular context while other tables are relevant for a different context. And the questions will be relevant to one specific context most of the times. So we'll use this method to cluster the tables using k-means clustering. Over here, I have chosen the number of clusters to be 7, but you can use the elbow method in order to find what is the correct number of clusters for your use case. Once we have fit the clusters, we can see which cluster, which is the different distribution of clusters. As we can see, this is very accurate as it is following more or less the databases format. So bank sales trading database tables are under one cluster, Austin tables are under another cluster, and so on and so forth. Once we have done the clustering, then what do? We want to identify which cluster is relevant for any question. So for a question, we'll generate the semantic embedding for that particular question, again using sentence transformers. And then we'll see using cosine similarity, which is the embedding, which cluster embedding using the mean of the cluster, which is the cluster which is closest to that particular question. And that very likely is the context of the tables which is relevant for our particular question. So using cosine similarity, we find the cluster which is closest, and using that we use the question embedding and the mean embedding of the cluster. Over here, we find that the cluster 5 is closest to our particular question about the airport distance. Let us see what are the tables in this particular cluster. It's airlines tables. That's a good sign. And over there, let's look at the specific one. It has the aircrafts data, airports data, and the flights table. All of these, the tables which we were expecting in the correct gold SQL as well. That's a positive sign. Now let's see if we were to use this in order to generate the SQL, does it actually give us the correct answer or not? So given the descriptions of the table, we wanted to write SQL using the tables and columns, and we give those particular table descriptions from the cluster 5. It generates an SQL. Let's compare this SQL to our gold SQL. It generates, let's open it in a different text editor. So it generates city routes using the flights table and merges on the airports data table on the departure airport and airport code, and the arrival airport and the airport code. This is very, very similar to what we were expecting. However, sometimes it may not give you the correct answer as we saw in the previous lab. Sometimes it takes the iterations in order to get the correct one. How do you overcome this? That's where DeepSeek actually comes into play. Let us ask DeepSeek to select the SQL which is the correct one. DeepSeek, being a reasoning AI, should be able to look at the SQLs and validate which is the most correct one. Once we ask it to do that, it generates an SQL, and voila, that SQL is very close and correct to the SQL that we were originally looking at, the gold SQL. So, what are the things that we have learned in this particular lab? We have found a new method that once we scale from tables around 14 or 20 to 150 or 200, we can go via k-means clustering and semantic embeddings to find which are the tables which are actually relevant. So schema linking becomes a lot easier with scale. Finally, we have used candidate discrimination to generate the correct SQL and make sure that we do not have to rely on the unpredictability or the unreliability of the LLMs. So we generated multiple SQL candidates by varying the subprompt strategies. Then we fed each candidate into DeepSeek, a great reasoning model which scores them on the execution success, semantic scoring, match, and cost. The highest scoring query goes into the production. So when you scale to 60,000 tables as in enterprise catalogs, you layer on GTR, graph table retrieval. It includes course clustering, TF-IDF similarity, page rank, and then a final GPT API call on the pruned set. This multi-stage funnel keeps latency and cost in check. So now let's make these techniques into modules and deploy them. So finally, we will build a lab that wires everything into a multi-model Rayserve blueprint. First, we'll have the deployment A, which is the metadata enrichment service, the table description model. Then we'll have the schema linking, the table relevance model. Then we'll have the chain of thought with SQL generation, the text to SQL model. And finally, the candidate description, which is the enhanced text to SQL model. Now let's go into the process flow. The user enters a natural language question via the web interface. Then the enhanced service receives the request and orchestrates the pipeline. It makes 5 parallel calls to the text to SQL service for multiple SQL generation. The text to SQL service calls the table relevance service to find which are the relevant tables, and the table relevance service queries the table description service for the schema info. All services read from the MySQL database for the table and column metadata. DeepSeek AI evaluates all the 5 generated SQLs. The best SQL is selected and returned with a detailed analysis. You'll spin up each service locally and expose a single query endpoint, stress test it using a web browser. So ensure you have Ray 2.x installed, a serve.yaml defining your deployments. With that endpoint live, you can route Slack bots or connect data warehouses straight to Rayserve. So now let's dive into the code. So the entire code base looks something like this. The main models are stored under source under models. The first model is the table description model. Over here, we'll need SQL Alchemy and MySQL connector. What we've done is we've connected Maria database. We use the table description model to serve as an endpoint where you can give the table schema and a new table data, sample data, and generate table descriptions that are stored within the database. Now, every single time you ask a question, it will refer to the table's data and the table descriptions that are stored already in this Maria database. Let's go through this just to be familiar with it. There's a table description model. It has the table database manager, which is going to access the database. You can set the credentials in the env file to make sure you can access it. We have the session maker, the engine. We have the column description, the table description. In the table description, it will store the column, the table name, the description, the sample size, total columns, when what was created and when it was updated. Similarly, in the column description table, it will have the ID, it will have the table of that particular column, it will have the column name, it will have the description for that column, it will have the data type of that column, when it was created and when it was updated. This is fantastic information to have to make sure that when you are asking a question, it has all the relevant information, and to make sure that the columns and the tables that are selected are based on recency. Finally, we save the table descriptions. And that is the function for saving the table descriptions. There is the function for saving the column descriptions. We can analyze the data types, and this is the create prompt. As you can see, this prompt is the same prompt we were using in the labs itself, in the Jupyter notebooks. It's just that we have made it into a modular code and allowed it to connect to a Maria database so that whenever you ask, you can fill it the database with tables, the new tables that you put in. If you want to specifically access this particular table, you can run it through the server. That particular file, start server.py, it will start only the table description model server on 8000 localhost, and you can client it using client.py, and you can access and fetch, like you can put in new table data and you'll see it reflected in the database itself. The YAML files are stored under config folder. Now let's move to the table relevance model. So the table relevance model, uses again SQL Alchemy. What this one is doing is that you are given a question. You are given what we've done is we've given a confidence threshold and the maximum tables. These are extra features that we are adding to tell it that at most please return 5 tables. So do not tell, like, the number of relevant tables is not going to be 20. Please, out of 150, like out of so many tables, do not return all the tables. And what we are saying is that in the prompt we are saying that create a relevance score, and then for each only return the tables which have the confidence score of more than 0.3. This will ensure that it does not return tables which are slightly relevant and not very relevant and get confused in that. So we have used this to create the relevance score. We have asked it to use relevance reason to justify why it is saying that as a chain of thought reasoning in the prompt, and finally return the relevant columns as well. So the code over here is just the modular code, very similar to what we had been doing previously as well. So we create the database manager, we get the table descriptions from the table, and use that to finally create the prompt. So the prompt is going to take the table information. It is going to take for each table, it is going to take the table name, table description, and the column information and the columns. And finally, it's the same prompt. So you are a database expert, you are going to find out which are the tables and columns which are most relevant, right? So you are going to, for each table, identify which column would be needed and provide the relevance score. And similarly, you are going to respond in a JSON format. You're going to respond with the table name, the relevance score, give a reason like in a chain of thought prompting. And you are going to give the column, for the column also the same thing. And finally, an analysis summary to make sure that the reasoning is correct. Finally, we will have to parse that and give the return the tables which are relevant. Now, if you want to specifically run this server, you can use the start table relevance server. This will start the server on the port 8002 localhost. And if you want to check it, you can use the tables relevance client under the clients folder in source folder. And that will allow you to give a question and see which tables it actually selects. Make sure that your question is in fact relevant to the tables. On the other hand, it will return that no table was relevant if you ask a question that is not related to the tables. Finally, we move to the third table, to the third model, which is the text to SQL model. This model will again use the OpenAI interface. We'll use the GPT 3.5 Turbo as we have been using. It will take the tables from the table relevance URL. So make sure that if you are running this particular model, that the table relevance model is also running in the server. So what it will do is, given a question, it will see how many maximum tables are going to be relevant for that question. What is the confidence threshold, as we needed that for the text to the table relevance model. We send that. So let's just look at the prompt that is relevant. So it says create a prompt using the relevant table information from the table relevance service. You are a SQL expert. Convert the following natural language question into an SQL query using the database schema information. So we give the database schema for the specific relevant tables that have been returned from the table relevance model. And this shows that. It also shows the relevance score, so that the table relevance score is going to tell how relevant a table is going to be for the final SQL query. So it understands certain tables are very, very important for that particular query and for that particular question. We make sure that in the answer, there should be an explanation, which is the chain of thought. It should tell the confidence, which is like confidence over how likely is that the SQL query we are asking the model itself, and then the tables that are being used. This creates the SQL prompt, and then finally it gets the response and extracts the SQL query to show it to the user. Similarly, for this, if you want to start the server, which will be started on 8001, you can start it by using the text to SQL server.py. And if you want to test it, you can use under the clients, you can use the text to SQL client.py. Finally, for the fourth component, which was the candidate generation, we will use the enhanced text to SQL.py. In this model, it basically calls the DeepSeek API, as we have discussed in the lab previous to this. It will call the text to SQL URL, which was hosted at 8001 port. It will call that URL and it will call it multiple times to generate multiple SQL queries. Now it is your choice if you want it to be iteratively the same thing, or you can make sure that between the different iterations the prompt slightly varies. So you are able to make sure that you are maximizing the randomness and you are getting the various different kinds of SQL queries that can be there to ensure that you select the final one which is the most accurate. So for this it uses a thread. It generates 5 threads at the parallel. Then for each of them, it calls the query, it calls the result query, and it calls for the executor the text to SQL service, which in turn will call the text to table relevance service, which will be using the table descriptions which were generated using the table description service. So it will generate the query ID, it will generate the best SQL query, the reason for selecting that, the summary, the overall confidence now, and the selected metadata that it had. So you have the detailed analysis. This makes the code very easy to scale as well as keep track and while debugging and ensuring low latency. Now, if you want to start this server, you will use the start enhanced text to SQL server, and for the client, you can use the enhanced text to SQL client. So this is if you want to start them individually. If you want to look at the whole thing, make sure that you have the env file using the env.example. Then you can basically run the quick start file. There is also the Dockerization which is possible. You can simply go into the Docker folder and run docker compose up build and it will generate the final link for the web interface. So over here, let's use the Docker compose. We move to Docker and we run the command docker compose up build. So it pulls the MariaDB that should be installed in your system. It's loading the different tokens. It's setting up the Python. It's collecting the Rayserve currently, making sure it is installed and set up. Then it proceeds to Panda installation, to MySQL connector Python installation. So in the meantime, you can look at the requirements file. There is the Rayserve, the OpenAI, Pandas, NumPy, Fast API, UVcorn, Pedantic. All of these are relevant. Let's just go through while the installation is going on. That the Rayserve is used for the Ray endpoint. OpenAI is for the prompt. The Pandas is for the storing the data frames and loading it in the table relevance model. NumPy is also useful for the same reason. Fast API is used in the app setup, same as UVcorn, also in the web interface and the server finally. Then Pedantic is also used for similar purposes. Then we have protobuf, grep ratio, and in the meantime we find that MariaDB has been set up. The server socket has been created on the local one. And the MariaDB distribution is ready for connection. So it is now going to, since the DB is set up, it is now going to set up the table description server, the table relevance server, the table text to SQL server, and the enhanced text to SQL server. So as you can see, the table description service is set up on 8000, table relevance on 8002, text to SQL 8001, and enhanced text to SQL on 8003. It has started each of the services and it is waiting for some time before the next service is started. One thing which I would like to mention is that in fact this code was created with the help of Claude and Klein and generative AI. As you can see that generative AI today is very, very helpful in a lot of ways. So finally, the enhanced text to SQL service has also been started. After this, once the services have been started, we'll set up the backend services and finally generate the web interface link so that we can click upon it and play and stress test it using our different questions. So let's just wait for a bit. There is also the README over here, which is very detailed and provides all the information as I had mentioned previously. So now the web interface has been set up, the server process is set up, the final enhanced text to SQL service is also set up at the local host, and the Uvicorn web interface is set up on the 8080. So let's follow this link and open this. So as we were discussing at the start, our web interface is set up. We can select any question, any sample question, let's say which is the find the most expensive order details. I will generate 4 queries and say that at most 3 tables would be relevant, and increase the confidence threshold to 0.5. Let's generate the SQL query. As mentioned previously, also it can take about 15 seconds in order to generate the SQL query. You can ask your own questions. It has generated the SQL query. Overall confidence is quite high, and there are a bunch of similar SQL generated multiple times, so you are sure that it is in fact the best one it can generate. You can ask different questions. Let's ask another different question. Let's say that what was the revenue of our top 3 products, and let's see what it does. I'm keeping the other parameters the same. So the number of SQL generated would still be 4. It's still in a MySQL database, so the SQL type will be the MySQL type. The relevant tables will be 3, and the confidence threshold will again be 0.5. So the SQL query shows select name, sum revenue as total revenue from your table, group by the name, order by the total revenue, show it in decreasing order, limited by the number of 3 rows only. So now we have built what we had set out to do, a text to SQL pipeline which generates the most optimal queries using LLM. So in these labs, we have seen how natural language question can be converted into a final SQL query. This SQL query can be attached to any of your data warehouses, be it Databricks, Lake, Snowflake. Once you get that, you can get the final data generated, and you can use any of your Power BI or BI Insights tools to generate insights from the data. There, your VP is going to be very happy, and so are your business leaders. You can use the following techniques for even enhanced performance. You can use fine-tuning for the table pruning by training a lightweight bamboo LLM model to predict the relevant tables. You can use RAG for the context retrieval by pulling in documentation or data dictionaries on the fly. You can even query onto non-relational queries by using the MongoDB or Elasticsearch DSL. Knowledge graph. Build a knowledge graph of joins and join IDs using previous SQL queries. Thank you for joining me in this deep dive. Now go empower your teams. Turn every question into an SQL answer.